time around, we're going to look at the internal forces, internal loadings developed in structural members. So all we want to see is what happens to a member when it is loaded. What happens inside. So here you have to see that if you had a beam or a member of some sort, and then it experiences some loading at some point, there are a number of things that are possible here. One, you expect that it's possible that this beam is going to experience some form of a rotation, or it will feel like it's trying to be rotated in some direction, and it will feel like it's trying to be stretched or compressed in its along its axis. And apart from that, it will feel as if at that particular point, as if there is a force that is trying to shear it or to slide just this part of it downwards. So we want to understand all those forces. Previously, under trusses and I think we had trusses and frames, we only talked about the internal force that was acting along the axis of the member. But now we're saying that it's not only this force that will be present inside this member, there'll also be a field of rotation inside this member. Hence the concept of shear force bending moment diagrams. So if we wanted to understand what is happening to this structure, to a large extent, the concepts we're going to use to analyze will be the method of sections. So because if the whole structure is in equilibrium, then any section of it we pick must also be in equilibrium. But of course, the first step before you even start picking your section is to draw a free body diagram of the structure. If the section you're going to pick is going to be just this part here, you might want to you might go on without drawing a free body diagram. But in most cases, the problems that you find will require you to be able to draw a free body diagram for the entire structure first. Let's look at the piece that we have here. If we wanted to draw the free body diagram on the whole structure, we notice that at point A we have a fixed support. A fixed support, we know to say that here there will be two reactions, one in each axis. So here we have the x-axis. We can assume, here again we're assuming. So for these reactions, we know to say that we first assume. So we'll assume this force will be, one reaction will be in the x-axis. So we have AX. And then we can assume that we have a vertical reaction. So this one, we can say that maybe it is going up. Again, you can easily guess that it is going down. That should be okay. So you have AY here. But being a fixed support, we know to say we're going to have a couple moment reacting to rotation. So we can set this to say it's trying to rotate the beam in this manner. So you can say this is going to be our moment at point A. So this is just a free body diagram at the point where we have that fixed support. But of course, we still see that everywhere else we have the force P1 here. And then we have that force P2 at the far end there. Once our forces have been sorted out, let's say we wanted to understand the forces or what is happening at that point B. So if we wanted to understand the shear force there, the normal force, and the bending moment at that particular point, what happens? We have to cut that structure, section it at that point. You see, if the whole structure here is in equilibrium, it should mean that even any piece of this structure we pick must also be in equilibrium. So that is where we're going to base our discussions on. Of course, in an event that you need to use the forces there and the moment there, before you even start cutting your sections, you might want to analyze the structure the way it is so that you identify or determine what AX is, what AY is, and what that moment is by just using sum of forces for the whole structure in each axis. Since it is in equilibrium, equals to 0. You can also take sum of forces in the y to be equals to 0. And finally, you can also take sum of moments to be equals to 0 since it is in equilibrium. After you have figured out AX, AY, and the moment about A, then you can move on to get your section. But again, I'm specifying you only want to determine what these reactions at the support, what they are, if the section you decide to pick for analyzing does need them. For example, in this case, when you section it at point B is, let's say point B somewhere here. So when you create a section about point B, notice that you then split this structure into two pieces. You have one piece which is to the left of point B. This piece will have the moment at point A. It will have the horizontal reaction at A, and the vertical reaction at point A. And the section to the right of point B, what will it have? So it says that section will have the force P2. It will also have the force P1. So this is what is on the diagram already. But what happens when the section is in place? With the section in place, now we say to maintain equilibrium, we need to add reactions here, we need to add forces here to just make sure that the effect of separating those, or let me just say, the forces which were internal at that point, by creating the section there, those forces will now be exposed and they become external forces. So here, for example, you expect you're going to have a horizontal force. You can guess whichever direction you want. You can assume it is to the right. But seeing that my AX here was assumed to the right, I'll assume the reaction here will be to the left. This force that is perpendicular to the section we are analyzing, this is the normal at that particular interface. Since this is at point B, that section was obtained at point B, so I can say this is, mostly you can just even label it the normal, but since it's at B, I'll say the normal at B. Apart from the normal, you're also going to have the shear force at that point. The shear force will be trying to slide this piece downwards. So here we can say the shear force, you can still guess that it's going upwards, but mostly here we'll be assuming it's going downwards there, and we're going to label it with the symbol V. Since it's at B, again we'll say the shear force at B. The last one is going to be the bending moment. But before we introduce the bending moment, I want you to notice what happens. For this section, if I say my normal is pointing to the left, it must follow that on the second section here, my normal, the same normal, must be pointing to the right. Because again, you should still obey Newton's third law. By the time you bring these two pieces together, even if you don't say Newton's third law, but by the time you bring these pieces together, at that point, the forces there must add up to zero, so that here, when you say the sections are brought back together, they get swallowed up, since they, in that case, they don't appear as external forces. So when you separate, each piece will have a version of that force, but when you bring them together, those forces must cancel out. So if NB on the first piece was pointing to the left, on the second it must point to the right. Notice that this is kind of similar to what we did when we are dismembering under frames. But here, of course, we are breaking the members, basically just cutting the member on the middle to, or at any point, to understand what is happening to the member at that point. Okay, so here the shear force to this member was, or to this piece, was highlighted to be going downwards. So to make sure that this is still satisfies equilibrium, it implies that on the other piece, it must be pointing upwards. But it's the same label, it's the same force. So even here, we'll label it the shear force at B. Now this is the tricky one, the one that tends to throw most students away, the bending moment. When you assume the bending moment at one point to be, or on for one of the pieces to be anti-clockwise, so if I assume here that it is anti-clockwise, so bending moment will say M at B, then it means that on the second part it must be clockwise. So again, notice this, when I draw this, this is anti-clockwise. To show clockwise, it must be this. So sometimes students here will think that because this is going this way, then to oppose that, then it must be this. Notice that here both diagrams describe an anti-clockwise rotation. They're saying the same thing. So if we wanted to show the opposite of this, we have to draw one that simulates a clockwise rotation like that. So here we have to simulate a clockwise rotation like this one. Again, same label. With this in mind, any of these sections that you pick for the analysis is fair game. Any one of them is going to be acceptable and it's still going to be correct. This is why I was saying that if you decide to go with this section where the reactions at A are part of the analysis, then you might have to find them first before you even start splitting the structure, the member apart. But if you're going to use this part, which does not have those reactions, given that P1 and P2 are given, notice that you can already find what the normal at B is, the shear force at B, and what the moment at B, without even knowing the support, what is happening at the support at A. So just wanted to point that one out. So before we look at our first example, you might be wondering what is the importance of knowing these concepts. One key application that I might point out here is that understanding these concepts might be beneficial in knowing exactly what is happening inside the structure. If you have a member that is loaded, it might be part of a structure which is being built, and then it has certain loadings at certain points. Maybe here it is supported, maybe it's a fixed support as we were describing on the previous one, and then maybe at one point here you have a loading. So there's a force that is acting. It might be at an angle or something, and then here there's also another load at the far end. Now you want to understand whether this member can actually withstand what is happening here. You want to know where is this member the weakest. You can just go through these processes to understand where you're going to have the maximum stress. Of course, this is going to involve some more concepts that you guys will learn as you proceed to third year and so on. But this is the first step in understanding the stress taking place inside the member. It will be the first step to understanding where this member will be the weakest. Where is it likely to break if it's going to collapse? So to an engineer, this is quite helpful. It will help you understand whether this member, each member part of a structure, can actually withstand what you're going to load it with. That's just from the top why this is so important. For our first example, we have this basic question. So this is just to help you understand how to approach these questions. So here we have a member that is supported at point A. So this member is supported at point A, and it is also supported at point D. So, and notice that at point D, we have, of course, the pin which is there. And when you look at this, it's like we have a couple moment which has been highlighted at that point. And then, of course, at A here, we have a rocker in place. Then there are 2 points which have been labeled point B and point C. And then somewhere between them, you have that 6 kilonewton force applied. So what are they saying here? They want us to determine the normal force, the shear force, and the bending moment acting for the first part to the left of point B, second part, and just to the right of point C. Okay, so we have those two two parts we're going to look at there. What's that of the 6 kilonewton force of the beam? Okay, we're going to basically just go with those to the left of point B, to the right of point C. Okay, so how do we answer this question? Well, same thing as we highlighted. First, you want to start with a free body diagram of the entire structure. So you have this. Start with what is given. Here you have point A, you have point B, and point C there. Then point A is here. Then you have D there. And then here you have the force there. This is not the force, that's the moment already present. And then you have the applied force right between B and C. Of course, the distance from A up to the midpoint of B and C. And then you have again the distance from the midpoint of B and C all the way up to where D is. 3 meters and 6 meters. Okay, so for the free body diagram, what do we do? First, we go to the supports there. At point A, we have a rocker. And you note to say that for that type of support, only one reaction will be present, and that will be a vertical reaction. We can assume the direction here, and we're going to assume vertical, going upwards. And then we have at point D. So at point D as well, let me try to redraw this one. So at point D as well, but this time we have a support there, but this time that is a pin. A pin will have two reactions, one horizontal, one vertical. So here, the vertical one, we're going to assume it is going upwards as well. This is dy. The horizontal one, completely up to us. We can assume to the left, we can assume to the right. Again, completely up to us. So here, we can go dx like that. So now we have included all the forces which are necessary for this part. Now let's start to answer their question. The first part, they want us to determine the normal force, shear force, bending moment to the left of point B. Point B is literally right there. So what are we doing? Our section must be cut to the left of point B. So basically, it's like we're coming right at point B, but just to the left of it. So we're going to analyze what is happening to the left of this point. So it's almost at point B where we are trying to see, but it's to the left of point B, just before point B. So meaning this force is not present. That is what they want us to do. So for this one, when we try to go for that section, notice that the easiest one to analyze, it's going to be this piece, this side, because this piece will only have this force as part of the discussion. But this side here would have multiple forces to analyze. But all in all, regardless of the section we pick, regardless of the side we decide to study, we notice that we have support reactions that are present there. So here, before we even put our section at point B there, we first want to understand what would be the reaction at A, what would be the reaction at D. Should we need this? Or of course need to find what it is. So let's try at least to know the reaction at C. At A, I mean. So what will it be? So to determine the reaction at A, what do we do? So we're going to analyze it before doing our section, meaning the normal force, shear force, and all, they are still internal forces. We will not include them in our analysis. So here we're only looking at these forces which are currently exposed. So here, if we sum forces in the x-axis, you'll notice that by summing forces in the x already, since it is in equilibrium equals to 0, you see that dx is the only force in the x. This has to be equals to 0. Summing forces in the y-axis, you have ay, dy, and that's 6 kilo. So that will still need a little bit more work. You notice that the quickest way to actually analyze this problem is to use sum of rotations, sum of moments. So again, you have to be smart here. When taking sum of moments at this point, I'm sure you guys have been doing this for some time, so you understand how it goes. You don't want to just take sum of moments about any point. Notice that you want to utilize the fact that when moments are evaluated at a specific point, any force that passes through that point will not cause a rotation about that point. Since I want to find AY, I don't want to take moments anywhere where AY is passing. So I can take moments about this point, can take moments about this point. But taking it about this point, I only eliminate a force I know, the only force I know. Based on that, the best place to evaluate our moments will be at point D. This way, this force will not cause a rotation at point D. This force will also not cause a rotation at point D. So we eliminate two unknowns already, leaving us with only one unknown AY to think about. So we'll take our moments about point D. So when we sum moments about point D and equate to 0, what do we have? Well, firstly, you have this moment which was already included there, that 9 kilonewton per meter. That moment was already present there. And notice that by taking moments at D, it doesn't eliminate the couple moment highlighted there. It just implies that the forces passing through that point D will not cause a rotation, but a couple moment is still active there. So we'll still include it in our analysis. We'll take anti-clockwise to be positive, and when you look at that couple moment, they're simulating an anti-clockwise rotation. So based on that, we'll include that as a positive rotation. Since I'm writing a 9 there, it implies that I'm going with a kilonewton for force. So that is already a moment, no need to say times distance, no need for that. So it's already a moment. What else? Now let me come to the 6 kilonewton here. Force times distance. It's already vertical. My distance, I'll get horizontal distance, of course, up to that point D. We said that distance has to be that 6 meter. So based on that, this is going to be plus. When you look at it, okay, so yes, when you look at that 6 kilo, it's also going to rotate our structure. Since it's about D, it's going to try to rotate our structure in this manner, meaning it's going to try to cause an anti-clockwise rotation about point D. So again, this is going to be positive. So this is a 6 kilonewtons multiplying a 6 meter. So notice that here I've kept the force in kilonewtons because this 9 had a kilonewton and a meter. My distance is left in meters because again I want a kilonewton here as well and a meter there, just like I had here, kilonewton and a meter. So just follow the units. You don't have to always write them, but be able to just keep track of them. Okay, that sorts out the 6. Let's look at the next force. The other force present is the AY there. AY is at the far end. It is vertical. So when you look at it, the distance from D up to where AY is going to be this one. So it's going to be the 6 plus the 3, giving us 9 meters there. But when you analyze the type of rotation here, this time this will be causing a clockwise rotation. Because that is a clockwise rotation, it's going to be minus. Clockwise would take it as negative this time. The force is AY, the distance is 9 meters, equals to 0. From here we have 9 plus 36 minus 9 AY is equals to 0. So now you're going to have 9 AY equals to, this is going to be 45. And finally AY equals to 9 into 45, giving us a 5 kilo. Because my force throughout had a kilonewton, even this one will also have that 5 kilonewton. It will also be the kilonewton there. So we have found what the force AY is. So having obtained the reaction there, we can now go and pick our side. So they want us to determine the shear, the normal, and the bending moment to the left of point B. So let's come to point B and cut the structure right there. So analyze to the left of this point. So what happens there? Let's get that piece. So point B, we'll just go up to point B. Include what is already present first. We already have AY at A. We already found AY. This is 5 kilo. What else? Now we have point B somewhere this side. So now let's show what is happening there. Since this was a member, we know to say that by breaking it between there, we're going to expose the normal there, the shear force, and the bending moment. So the shear force will always be parallel to that section. So take it to be pointing downwards. So this is going to be the shear force. We're going to go for B there. So we'll say at B there. Next, the normal force, we'll take the normal this way. And finally, the bending moment, we'll assume anti-clockwise. Okay, so this is what we have. So let's get this and analyze it. So for this part, the distance, of course, that we're going to use, before maybe we go to the distance, let's do what is straightforward first. When we sum forces here, we see that a few come out automatically. When you sum forces in the x-axis and equate to 0, again, since the whole piece is in equilibrium, any piece must be in equilibrium. Sum of forces in the x, we only see one force in the x-axis. So here we see that that force NB must be equals to 0. So in this case, the normal force is actually 0. Okay, so having found that the normal force here is going to be 0, we now want to find the other force present, which is the shear force. The shear force is in the vertical axis, so some forces in the y and equate to 0 as well. The 5 kilo is going upwards, that will be positive. The shear force is going downwards, so that will be negative. This is equals to 0. So here we see that the shear force will actually have to be equals to 5 kilonewtons. So shear force has come out as well, 5 kilonewtons. Now the only thing left is the bending moment. So to get the bending moment here, you're going to need the distance. The distance from any of the edges, basically wherever you're going to take the moment about, you need that distance. So where are we going to take the moments here? So for simplicity, we're going to take the moments right about point B here. But we need the distance to point B. So here the assumption is that B and C are right up to, or at least close enough to that point, so that we can just use that distance, which is 3 meters. Based on that, if we take the distance from A all the way up to B as 3 meters, and say we're going to take moments about point B, what do we see? So firstly, we already have a moment there, the shear, the bending moment itself, which is anti-clockwise, so we include that. And B, it's anti-clockwise, so take it as positive. Next, you notice that the shear force here passes through B, so it will not cause a moment about point B. The normal also passes through B, so it will not cause a moment about B. But the 5 kilo, however, does not pass through B, so it will cause a moment about B. So in this case, we have to include the 5 kilo. So the 5 kilo is going to be causing a clockwise rotation. So we're going to have a minus, but multiplying what distance? So we need the distance from the 5 kilo, which is point A, all the way up to point B. So this is why we're saying we'll use that 3 meters. So they're the only two, so this has to be equals to 0. We now have the bending moment, minus 15 is equals to 0. And finally, the bending moment, remember the 5 had a kilonewton, so this is going to be 15 with the kilo newton from the 5. The 3 had a meter, so with a meter from the 3. So this becomes the bending moment about point B, to the left of B. Okay, so this is how we analyze it in this case. So the next part is now to understand what is happening just to the right of point C, meaning that now our section, you see, if we end up getting the section to the left this side, if we end up getting this section, it will mean that we'll have to use the reaction forces at point D there. But we don't want to start finding them. You can, that's okay, but you can still just stick to one side. So here we'll stick to one side, but the same to the left of C, meaning we'll exceed B and come closer to C there, so that we analyze what is happening just to the right of C. So we'll go all the way up to C, but just at C, and then come back this way and here, so that we still keep on using the support at A, which we already found as 5 kilo. But notice one thing now. If we're going to the right of C, it means that this 6 kilo is fair game because it is applied to the left, just to the left of C. So that one will be fair game. So we're going to include it in our analysis this time. So notice that in this case, this is to the left. Our section has been cut to the right of C. So everything to the left of C will be part of this section we have selected. Had we gone for the section to the right of C, it will mean that it would have meant that to the right of C, what would have been present would have been first the supports at D, dy, and dx, and also this couple moment here. These are all to the left or to the right of C. So these would be the ones we would have had to work with. Notice that the 6 kilo is to the left of C. So we wouldn't have had it if we had gone with this. So with this, it would have meant that I would have had our shear force. Here, the shear force would have been going upwards like that. This is at C, we'll go with C. The normal force would have gone like that. And then finally, the bending moment. So this is how it would have been. But now we're going to the left of C. We're going to use the section which is to the left of this. Again, we are analyzing to find what is happening to the right. But the piece we're just using is this leftmost piece. So don't confuse the two statements. So at C here, we're going to have the shear force will have to point down. The same magnitude as that here labeled as VC, meaning even here I'll label it as VC. The normal, here the normal is to the left, meaning here the normal will have to be to the right. And finally, the bending moment. So this is what we have. Again, you can use any one of these structures to analyze your circuit. Any one of them will give you the correct answers. They'll give you the same answer either way. But in this case, we don't want to start calculating the reactions at D. So to avoid calculating the reactions at D, we'll pick the part which has the 5 kilo for the reactions at A since we already have it. For practice, I'll ask you to see if you can analyze this later on and see if you can first find the reactions at D. After getting the reactions at D, try to see if you can come back and use this piece now to determine what the shear force at C, bending moment, and the normal, what they're going to be there. So try to see if you can do it from that angle. But here, we're going to use this piece. So just like before, when you sum forces in the x-axis and equate to 0, so in the x you only have n at the normal, which is automatically going to be equals to 0. In the vertical axis, you have the 5 kilo going up. So the 5 kilo goes up, but you have the 6 kilo going down. You see that now you have 3 forces in the vertical axis. The 6 kilo going down and VC also going down. So that now when we analyze this, you have -1 here. So that finally VC will have to be equals to -1 kilonewton. Then when we sum moments, so take moments about which point? Again, we're going to take moments about just where the internal forces are there. So take moments about C and equate to 0. So about C, what we have, first you have the same moment there, MC, that is anti-clockwise, so it will be positive. Then next, here you have this, of course, will cause nothing, this will cause nothing. So you now only have the 6 kilo and okay. So we already saw that MC here, that moment, the bending moment is anti-clockwise, so it will be positive. So we have two more forces, this one here and this one here. This VC and the normal, of course, those are not going to cause anything. But remember, the point C is close to to where the 6 kilo is being applied. So let's go to the diagram again. So here the assumption that B and C are literally right on that 3-meter mark from point A. So this 6 kilo, it's like it's basically a passing right at point C as well, if we take that as that route there. Based on that, the 6 kilo is literally right on point C, or right at point C, and because of that, the distance from C to the 6 kilonewton is going to be 0. So the 6 kilo as well, we can assume it's passing through point C, so it's not going to cause a rotation about C, leaving us only with the 5 kilo here. But for the 5 kilo, you have to see that it will be causing a clockwise rotation. So it's going to be a minus 5 kilo, multiplying the distance from C, 3 meters. So it will be multiplying 3, and will equate to 0 there. So when we do the math here, this will be MC minus 15 is equals to 0. So that MC will be equals to 15. Don't forget, the 5 had a kilo, the 3 had a meter, so the 15 here will have the kilonewton meter. So this is going to be our bending moment there.